Okay,
Yep.
thank you. Thank you very much. May I continue with my second part, which is a little bit more technical. The first one was just to adapt to my accent and to provoke some thoughts. I will not give you answers now, but I would like to mention. So this is kind of introduction to my course on foundations of artificial intelligence. And it is mostly about machine learning methods. And in my course, in the lectures, I speak a lot about neural networks, different kinds, multi-layer perceptron, probabilistic neural networks, recurrent neural networks. We have deep neural networks, convolutional neural networks. We also have statistical methods like support vector machine, Gaussian mixture models, hidden Markov models, regression, decision trees. These are the topics we discuss in the foundations of artificial intelligence. And of course, we are going to talk about intelligent agents. All these machine learning methods are actually components, modules of the intelligent agents. It will be quite challenging to explain things without showing equations and formulas and some engineering schematics. But I would like to remind you the engineering perspective of everything. So we aim to build agents that act intelligently so that they are useful. So an agent should be doing the right thing based on what it can perceive and on the actions it can perform. What is the right action? What is the right thing? This is a very strange question, because as an engineer, I would say that the right action is the one that will cause the agent to be most successful. But that's really scary, isn't it? So we engineers like very much performance measures. This is some objective criterion for success that we implement inside of the agent in order the agent to be able to assess its own behavior. And what is important here is to define very clear performance measures, things that the agent could measure on its own. The agent is an intelligent creature that can sense the environment, can interpret information, can also make decisions based on its knowledge, its past experience, the modules implemented inside, and the decision made are then implemented as actions. So if I have to describe what is an agent, I could really show two boxes. The one box is, let's say, some creature. Agent could be a human, animal, machine, some piece of software that is doing very simple thing, perceives the environment through some sensors, makes interpretation of this information, and then converts these perceptions to actions. So agent could be everything that is autonomous. The important part here is that the agent has this function to process information and to make decision for its own benefit or for the benefit of his master. So what an agent can do? The agent can perform actions in order to modify future percepts so that to obtain useful information. This is the information acquisition process. And an agent is autonomous if its behavior is determined by his own experience. Of course, an agent needs to be able to learn, to adapt, in some cases, to create things. There are agents that create art or agents that create poetry or paintings or music. These are things that already exist. What is a rational agent, however? That means the agent for every possible perception or sequence of perceptions to select an action that is expected to maximize the performance measure given the evidence provided by the observation and the knowledge it has at this time. So a rational agent is doing what is right, that something that leads to a benefit, to a specific goal, if there is goal defined. If there is no goal defined, to specific utility or to specific goal. When I'm talking about agents, I always say that agent is some piece of hardware plus some software. In order to summarize, I would say that an agent can perceive the environment and do a range of actions. So, how the agent is doing all that? Of course, the agent is using some sensors to perceive the environment. What kind of sensors? It depends on the application scenario. We humans have 5 types of sensors, and we do everything with these 5 types of sensors. But machines are not restricted to those 5 types. Besides the visual, touch, audio, they can also have sensors for radiation, for ultraviolet. They could have sensors for distance that work on great distances, and they could have everything else that we cannot imagine at this time. But the perception comes from the interpretation of this information. And perception and observation are different things, because the interpretation of information depends on knowledge and the context of the observation. So the agent can use some performance metrics, some models, and some strategies to make decisions. And then decisions are implemented into a specific set of actions. What actions are possible depends on the actuators this agent has. We have hands, we have legs. With these hands, we can manipulate objects. With our legs, we can, let's say, go from one location to another. We may have other actuators to do other things, but probably we don't. Speaking about agents, I will also say that this is very well described in the book of Russell and Norwick, that agents are also software. And there are many categories of actions, of agents. There are many categories of agents described in this book. And the simplest is reflex agents. Agents that simply react to some external factors. Something happens and the agent is doing something else. These are rule-based systems or lookup table-based systems or some simple technology. And then there are more complex agents that also build model of the environment, so they can react to observations of the past. I mean, they accumulate some experience, and when there is missing information, they can implement decision based on the module. And then there are agents that implement specific goal. Let's say the autonomous taxi. When I go to the taxi, I say I want to go home. Okay, and then the taxi knows that I'm Todor and my home is somewhere, and the goal is to transport Todor from point A to point B. There is a clear goal. But then there are other agents called utility-based agents. And then this utility means that the agent is trying to be useful. So such agent could be ordered to make Todor happy. So the agent should know me very well and find a way to please me in this specific moment. Usually such utility-based agents cannot be described very precisely as a behavior, but they will be doing the best effort to be useful up to the limits of the situation and the context. So utility-based agents are trying to be useful, and they have a mechanism for assessing how useful are they at specific time. And they have strategies to improve this based on the environment and the options they have at the specific time. And then there are some learning agents that all the time adapt from their experiences and that really can learn new functions. And these learning agents are our instrument to develop the general artificial intelligence. That means that if I train a robot to walk on Earth, when it goes to another planet, it will still be able to walk regardless of the different terrain, regardless of the different gravitation forces, regardless of many different components. For example, maybe no air, or maybe dense atmosphere, or maybe some other strong winds. Agents that learn are a step closer to the general artificial intelligence. We humans are very close to the general artificial intelligence. I would say intelligence only because artificial doesn't sound very nice. We are close to the general intelligence because we are able to do things for which we were not trained in advance. We figure out how to do things which are new to us. For those who want to learn more, chapter 2 of the book of Russell and Norwick really gives a very, very nice description. There you can read about a vacuum cleaner like the iRobot we own in our homes, maybe most of us. So it explains in a very clear and nice language what are the problems this vacuum cleaner has to do, how it avoids the obstacles, how it implements its goals. And there are new advanced modules, of course, that can be trained to avoid specific parts of the city, of the home, for instance, where the pet sits. So the pet doesn't want to be disturbed by the robot all the time. And the robot can learn that this part of the home is not really permitted, and many, many other things. Just as example, I would like to show you the internal structure of an agent which is module-based and utility-based. Here the utility is some cost function which combines different performance measures. For instance, one performance measure could be how fast the vacuum cleaner will clean the home, the entire home. And the other would be how much energy will be needed. And the other one will be how noisy this robot will be. And the other one, how much time will take. And the other one will be something else. We have many different criteria, some of them conflicting, and these criteria are unified in a cost function. And thus cost function is evaluated on every step. And then based on the current situation of the world, the environment, the robot has sensors, and through these sensors, he is able to, or it is able to answer the question, what is the state of the world right now? And then based on the previous experiences, the robot can understand, oh, I was in state 2 and now I'm still in state 2, or oh, I have to move to location B because here is already clear. And based on the observation, the robot can know that he has to do something, has to pass from one state to another state. So here we implemented a state machine that has a finite number of states. This is kind of simplification, but for simple problems like the vacuum cleaner, it works. And then in more complex systems, we have a model which explains how the world evolved. What is the current situation? What is the current state? And what is possible to happen on the next steps? And then the agent is able to answer the question, what will be if I do action A or B or C? I have a list of actions that I can do as a robot, and then I evaluate what will happen if I do action A or B. So there is a model that really explains what specific action will cause to the environment or as consequences for the behavior implemented in that way. And based on these models and based on the answer of these specific questions, then the agent can evaluate how useful will be by doing action A or B or C. And then comes the question, how happy I will be in such a new state provoked by my actions. Would I be happy? And if I find action that satisfies this condition that I will be happy, why not implement this action and try it? And then on the next step, the sensors will give me information. Did I succeed to be happy? No. So I continue. And then I continue evaluating these conditions. And maybe I update the state, or I update the modules, or I really select different working point of this utility function, because these are things we can manipulate. When I start talking about probabilistic neural networks or Bayesian networks or some other classifiers, I would mention this, that, okay, very nice. Utility is a function, but we can select a specific working point at that function and operate in order to deliver some comfort or to deliver more security or to deliver something else or to balance between those. I will not go too much into detail, but many of these boxes are actually classifiers, or at least some of them are classifiers. They consider making decision based on some information. What action should I do now? It is a classifier that considers all the possible actions based on the available information from the previous stage. How happy I would be in such a state. This could be some regression element that evaluates the degree of happiness according to the specific cost function. So we will speak about some of those modules a little bit later, as they will be implemented with machine learning methods for modeling or for decision making. Another example could be the agent that learns. This is a general diagram of learning agent. And then the entire agent that I showed you in previous slide is now just one box here, the performance element in the new learning agent. Of course, we have the sensors, we have all the functions implemented above, and then we actuators and implement actions. But then in the new agent, we have mechanism to receive feedback. How successful is the agent? According to some performance standards that are given to this agent, it can really decide, do I need to learn some new functions? Am I successful? No, I need to learn some new functions. And then what functions to be learned depends on the learning element, who suggests changes into the modules, exchanges knowledge, and in some iterative way adapts the modules or the decision-making process. How is doing that? Through a problem generator that is a generator of situations, generator of data that help train the modules here inside in the performance element so that they can implement new functions. So we have a general structure of agent that is able to do things and learn by experience while operating in the environment. And of course, we humans do similar mechanisms. We are doing our job, but then comes the boss and says, you should do this faster. Okay, so I'm adapting some skills based on the critique I received. I have specific feedback, and then I know that I have to develop some new skills. And then I start following some courses or some exercises, and with the help of those, I train, and adapt. And at some time, I'm working faster. Or if my boss comes here and says, you should work twice longer that you work now. This feedback will be, okay, I should work twice longer. Based on the learning element and the performance element, I will probably realize that I cannot work twice longer, but I probably can work twice more efficient, and will probably adapt to some new functionality. I will develop some new functionality so that I work twice more efficient and achieve 2 times more. It is equivalent if for unit time I can achieve 2 times more or work twice longer, probably for some specific cases. But this mechanism is general. It is implemented in agents. It is somehow implemented in our kids because they have the performance standard at school and they learn new knowledge. And it is not that strange that robots can do things like that. And hopefully one day we'll do this more successfully than we do. And speaking about the hardware, I again use image from Russell and Norwick, which is very nice actually, and shows the abilities of a human and of a computer. just like numbers. Things look very similar. Nowadays, okay, this information a little bit old, 2019, but let's say it is correct for today. Computers already have millions of GPUs and CPUs, millions. It is almost the same like the number of columns in the human brain. These are maybe the smallest units of the human brain. Number of neurons propagate together, operating on the same data, and they form columns. Actually, sometimes many neurons can create one column, but if we consider the neurons as elements of the human brain, then we should consider the transistors of the GPUs, because one processor can have billions of transistors. These are the switching units that make decisions. So if we compare transistors with neurons, we see that computers have more instruments than we do. And then comparing the memory, we have only 10 on 11th degree of neurons. And now the memory of computers is much more. And then they have internal operational memory, and then they have hard drives with extra memory. And computers are much faster. Nowadays, computers operate on gigahertz. And then humans usually operate on several hertz, or in the best case, in several hundreds of hertz, or in specific activities up to 1 kilohertz. These are the brain waves that can be detected with electroencephalogram. So what is the result of this? Computers can do more operations per second that humans can do. This is not the case for our personal computers we use, but it is already the case for supercomputers. So as hardware, we could say that today supercomputers have small advantage. What is not clear is the software, but this is coming. Software is getting better and better, and very soon software will be able to learn on its own without the human help, and that's the great problem, actually.
Professor, there is a question from Alexandra.
Yes, thank you.
Yes, excuse me, I have a question here. How useful is it really to compare the brain with the computer? Because to me, it always seems that this is a bit comparing apples and oranges. If I compare my brain with a computer, I do know that computers, for example, cannot forget, but forgetting is a very important brain function.
Exactly.
Computers have no capacity for unlearning, but unlearning is a very important human function. There is no neuroplasticity in a computer, but there is neuroplasticity in a brain. So maybe brains aren't as fast, and maybe they can't store as much as many pieces of information. But still, I would think that by their nature, they are the better tool to make decisions with, because of things like neuroplasticity and unlearning and this capacity to take experiences and form new synapses. And I really, what's the advantage of comparing a brain with a computer?
Actually, what you said are disadvantages of humans. We need to forget in order to move on and to be able to cope with these limited resources we have. And we forget our best memories, and someday we have the problems with the loss of important information. So what you said, to my opinion, is that we have a mechanism to cope with the limitations of our brains. And to forget sometimes is good. If you forget emotions, it could be for good. But if you forget important information in order to rediscover it later on in slightly different form, this is waste of energy. I think it is already proven that computers are very good at recognizing objects much better than we are. I will give you an example. For many, many years, I worked on speech technology, creating speaker recognizers. These are systems that can recognize humans by their voice. We humans are very efficient in recognizing voices, but only for the few people that we know very well. These are our relatives, our friends that we meet every day. Sometimes on the phone, we cannot recognize people that are, let's say, our former colleagues or some friends we didn't see for 1 or 2 years. These are our limitations. A computer can really recognize thousands, many thousands of people by their voice. Once, if the computer is trained, most probably this model will be kept forever. And if the voice evolves with the age or with other reasons, the computer needs very, very small adaptation to continue. If computers were able to remember only 5 or 6 voices as we do, voice banking will be impossible. So it depends on the perspective, but I don't believe that forgetting is for good unless we forget negative things.
Yeah, but what are the implications of a computer not being able to forget negative things?
Oh, that's very dangerous. The computer will become evil at one point because he wants to take revenge for the past.
Yeah, but is revenge not a human thing? Shouldn't it be totally without judgment for the computer whether something is negative or positive? I mean, this idea that a machine can have a value judgment to a piece of information is what I find difficult, because a computer sees data of a person saying something negative to another person, but to the computer, it's only words. I don't think that there's this emotion that flows with it. So how does the computer decide what's good, what's bad? And you know what I mean?
Yes, of course. Computer has no notions of good or bad. Even we humans do not have a common understanding what is good or bad. We differ quite a lot in different cultures, in different religions, in different places. What is good or bad? I believe that animals do not have the notion of bad. Even some humans, some tribes do not have the notion of what is bad. It is cultural. This comes with religion and with society. And it will be quite confusing to explain to a computer that something is bad in Bulgaria, but is not bad in another place. These are habits, behaviors, all the cultural differences we overcome somehow when we get used to each other. But these are problems, ethical problems, moral problems, social problems, even legal problems. We humans are very often misbehaving because of the local context. Imagine how to explain this to a robot. A robot, artificial intelligence, learns by experiences, by observation. They learn what they see and consider it normal. Of course, we can say the 3 laws of robotic. A robot should not harm a human. But what does it mean to harm? Maybe by killing one, the robot will save thousands. Is this good or bad? These are human abstractions that are even different. I would say it again. Even we humans do not agree sometimes. Imagine in the court, when you have, let's say, dispute or legal case with your relatives or with your friends or with your colleagues. There is one fact and many different interpretations, and even we humans face difficulties to deal with that. This is the greatest problem with artificial intelligence, and this is why I do not want to create artificial humans. Nobody wants, actually. We don't want to create more problems. We want to create machines that help us solve specific problems, that help us improve our memory because we are not very good in memorizing things, to help us make decisions because at some point, computers will be able to make responsible decisions. If we manage to explain what is good, what is bad, what is ethical, what is not, what is legal, what is not, the problems now are not in technology. The problems are in ethics, in philosophy. This is the most difficult part. And you say forgetting is good. Maybe, because when you do something bad and you are a criminal, I mean, if I'm a criminal and do something bad, I know that after 3 years or 5 years or 10 years, it will be forgiven by everybody, even by law. So I can do something bad, and then for 5 years I will hide somewhere, and when I'm here back, it will be forgiven. Is this good? I'm not sure. Maybe it is good, because in 5 years I will be another person and I'm not the same. I don't know. These are questions I cannot answer, really.
So do you think that artificial intelligence's biggest challenge is actually finding the proper field of application? Because people so often try to apply it to every aspect of their lives. And I think that there's a lot of aspects that should be reserved for human decision-making. I have some experience with systems that are used for hiring processes, for example, and they come up with rather questionable decisions so far. And they have a negative impact on the entire human resource management world, in my opinion, because they take out the element of discovery. You know, very often when you just reduce a CV, for example, to certain aspects like what kind of university degree does that person have, what kind of work experience does that person have. The idea behind these systems is that they find the best match for the job. But I think that this is a very unlikely setting, because the best match for the job might just be someone with a different set of experience that was not programmed into the search. And then what do? You end up with, you know, mediocre decisions at best.
Yeah, it is very nice question, actually. What I could say is that if you use technology as instrument just to filter out some information, just to keep those subset of CVs which is somehow matching the position, and then do the rest manually, you're on the safe side, because you simply use the instrument to narrow the subset. I would help you in a way to figure out the next step. Now you have an instrument that is able to make a match between some CVs and some persons. But then the next steps come to implement artificial intelligence methods that help evaluate the mental capacity of a person. There are some tests already that measure cognitive capacity, and then some other tests that measure the stress management capacity of a human. And then there are some genetic tests, and then there are some tests that test the decision-making capacity of a person. This is very easy to automate today. Imagine that starting a new job, you have to sit on a computer and pass several tests, and then you are told, okay, your CV is a good match, but then I see that you are very impulsive, and then you see you have somehow negative attitude, and then your cognitive capacity is not high enough to take this position. I mean, this is very frustrating if you're not given the chance by the human relation officer who is hiring you. You are not even given the chance by technology, because we have systems that can evaluate the mental capacity and emotions, and this is reality now. Everybody now has this smart watch. You know, the smart watch is measuring your surface. I know you have it. I know everybody does. And this is on your hand now, so we can monitor your heart rate. Oh, it is not. This is good. So we can monitor your heart rate, and based on your heart rate, I can judge your emotional condition, your stress level. I can judge the heart rate variability, which shows your cognitive load right now. And I can also measure the skin conductance through this watch, and many other parameters, which helps me to read you your current state, your state at this moment, momentary state. And then by showing you some stimulus, I can really very fast make decision what is your current situation, and then can put you in situation of risk or in some, let's say, provocations, just to measure your reactions. This is not the right direction, really. I fully agree with you that machines should not be involved in the hiring process, because this is kind of fascism, I would say. Discrimination based on, oh, I hope this is not my future, really.
It's kind of a discrimination based on a person's ability to fit a mold.
Yeah. So this is not good. It is a possible future. We are working on that, believe me. But this has also nice applications. If a collaboration between robot and human needs to be efficient, you need to know the momentary state of the human, because collaborating with a robot also has some risks, the human to be injured, or you know, we can measure if the human really is concentrated or not, the degree of concentration. And in this collaboration between robot and human, if the human is not concentrated, this means several things. First, low efficiency of this collaboration. Second, high risk of errors and injury. And if we want to make intelligent system, artificial intelligence or robot, it should be able to read the momentary state of the human and to protect the human. Or if you have this robot at home and your child is violent, what the robot should do? I would suggest the robot should go to the bathroom and lock himself inside. That's the clever thing. Everything else will be wrong, I believe, because of the interpretation of the situation. Humans have different behaviors as kids, as adults, and For the robot, it comes too complicated. So the best thing is to go to the bathroom and lock the door and stay there until the parents are back.
I think Angel has a comment or something.
Yes, please.
I wanted to comment on the hiring application for the artificial intelligence. I think this is very wrong, because the end game of artificial intelligence should be that we should not work at all. So
Angel,
I like the approach, Angel.
there are some dangers. You probably have read the book The Time Machine of Herbert Wells. Did you?
No, I did not.
I recommend The Time Machine. Please read it. It is 100 pages. It will not take too much time. This is a society. This book is written 100 years ago, by the way, but there is the human society which does not work there. It is free of labor. Just read about the implications. So I see Angel is here, but I still have few slides to go. May I continue or we stop here?
No, please go ahead.
No, please.
Okay, so thank you very much for giving this chance. And when we talk about decision making, there are really many different tasks of decision making. And in this slide, I try to summarize whoever wants to learn more about that. I have a very nice book written on the subject. It is called so just give me a second. Computational bioacoustics. Computational bioacoustics, and it has very gentle introduction to people who are not engineers. But in general, we have several different tasks to solve. The one approach is to reduce every problem to a two-class problem, where the one class is our target class, and then we have everything else which is not interesting. And then we can do one class detection. We detect only one thing which is important, a key indicator. This is much more simple than the multi-class decision problem, where we have a complexity. We could have identification of multiple objects or of multiple events, and sometimes we have multi-label items. That means that the same object can have different tags depending on the perspective that you are looking at it. And then if we stay in the two-class decision problem, we can have either detection task or recognition task. How the recognition is different? Because we take time into consideration. Recognition is usually a sequence of events and their timestamps. What happened when for a specific time of events. And then there is the task of localization and tracking, how the source of information moves around in the space. This is very important for tracking of objects, for the military, for the air traffic, and also for us, the humans. And if I want to design a robot that follows the sound source and move its face to the sound source, this is also quite important. And of course, there could be even greater complexity if we have several objects that are in one category. We have one group of classes that involves many different objects. For we humans are very good in this. If I see something flying, I would say, oh, this is a bird, or oh no, this must be a drone. But for me, bird is a large group. It could be any kind of species. It could be whatever bird. For me, this is a bird. We humans, when we see through the window, we say, oh, this is a tree. But trees are many different trees, and they could look kind of different. For us humans, it's quite simple to recognize categories, but for the computers, it takes significant effort. And we have many other situations. In my slides, I usually give examples for one class detection or for target class detection from the perspective of the user. Imagine a system that can recognize birds. So I keep one recording of a bird. I provide it as file name to the system. And then based on the module for this species, the system decides, yes, the species sounds were detected inside of file name, or no, the species you target was not detected into the file name recording. That's a very nice way to explain things from the user perspective. But then if we have identification, that means multi-class decision problem, then the user says, okay, this is my recording, I provide the file name. Which species is this? I'm not asking if the species X is present. I already want to know which one is this species. I don't know really. I want, and if the computer already has a model for this species, the system can return answer. Okay, in your recording, there is sound of species sparrow, for instance, or the computer can return answer, none of the species that are known were found in your recording. That means in your recording, you have species that computer doesn't know. But in this case, a computer has number of modules and have to select one module or none of them. In the previous case, you have just one module of the target. And there are many other things which are specific for the machine learning community. I will not go into detail because this is beyond our time today. But if you follow my course on foundations of artificial intelligence, you will be able to get familiar with those things. The next big thing I want to say is that decision making is not that easy because of the free lunch. There is no free lunch theorem. There is one theorem that says there is no free lunch in machine learning. And it means that there is no instrument which is best for all the tasks. And we categorize the instruments in different approaches. Some of them are discriminative approaches. They simply try to separate data into two categories, either the target one or everything else. Or there is the generative approach where we build models. We try to estimate the intra-class variability of data. Why this is important? Because we can indeed say, okay, this is class 1, but here we have extra opportunity to estimate the probability of being correct. That means with the generative approaches, we have a mechanism to provide the confidence of the classifier. How confident is the classifier for the specific decision? And what is different here is how the classification is made. In discriminative approaches, we simply decide with respect to a boundary. And then in the generative approaches, we estimate probability based, okay, probability is too inaccurate. We estimate likelihood. That means probability based on observation and model. And based on this likelihood, we try to estimate the probability of some unknown data belonging to class 1 or to class 2. And this is much more interesting because it brings extra information. I mean, one thing is to say it is class 2 because I say this. And the other thing is to say, okay, it is class 2 because I believe that it is 60% probable to be this. The second has a little bit more information, right? And in my course, I also speak about classifiers of the two categories, multi-layer perceptron neural networks, support vector machine, decision trees, and so on. And we also will discuss classifiers like probabilistic neural network, Gaussian mixture models, Bayesian networks. These are different approaches to implement models, either non-parametric or parametric or probabilistic. All this in my slides and the labs prepared by my colleagues. And when it is about decision making, we also have to consider that decision is based on data. And depending on the data you have for module creation, we can achieve different performance. And for instance, if you own very few data and try to use different instruments, these are different instruments, deep neural networks, which is very fashionable now and hot topic, and traditional machine learning means these are these statistical methods I mentioned already, and some other neural networks. Which is the best actually depends on the data you own. For very few data, most probably some of the traditional machine learning methods, I would say probabilistic neural network would be best. It can start classification just by one example. If you provide one example for every class, it starts to operate. If you provide a little bit more data, it will start working better. And then more and more data you have, it will improve slightly. But traditional machine learning methods are very good with limited amount of data. And when you have more data, you can try the different approaches and see which one is more appropriate for your application. And when you have plenty of data, you can really go for deep neural networks because they can really learn from your data. They can learn the representation, the content of your data, while the traditional machine learning methods actually depend on constructing features manually. A human looks on the data and based on his experience decide to extract spectral or temporal features and designs some subset and then uses this subset for the modeling and decision making. When plenty of data are available, deep neural networks are able to figure out which are the important features on their own. They discover the features also, and this helps them to achieve much higher accuracy, performance, I would say. And here comes the question of responsible decision making. I mentioned this already several times, that decisions are made based on models, and models are built based on data. So in order to make responsible decision making, we need to carefully select data, the examples we show to the computer, and then it's very important how we tag this data, how we label the data. And then comes the model development. Of course, if you have trash in, you will get trash out, unreliable decisions. Okay, responsible artificial intelligence means, first of all, to be very careful with the data you use for creating the models. But then, as you noticed in our discussion, we have ethical, moral, legal, and many other considerations that have to be implemented in the decision-making process, so that from the many possible outcomes, we select the one which is acceptable from human perspective. That means to be responsible. the decisions made by technology to have effects that are desirable for humans. Of course, responsible decision-making is much more than that. There is a science called responsible decision-making. It is part of the social sciences, and they always consider consequences of a decision. So responsible decision-making should involve ethical, legal, cultural, and socio-economic values and incorporate them in the AI technology. And artificial intelligence and the machine learning method that support should be comprehensive, explainable, ethical, and efficient. It is very important that humans understand how technology works, and so that technology is predictable. Humans are very much afraid of something that is not predictable. This is why humans are very much afraid from foreigners or from humans that come from different social environment. It is a reflex. If you are not predictable, you're danger, right? And there are many other things. I will not read through the slide for you. Probably you will be able to see this when the slide is online. I just want to show examples of one-class detector, what it actually means. We have some repository of data. This example is for pest detection, detecting of one pest that eats the palm trees. This is great danger in the past 20 years in Mediterranean. And we had a project on that, trying to diagnose which palm trees are infested with this worm, and then those that are infested are cut and burnt. Okay, in this specific case, it is important to make the right decision because a palm tree could cost 40,000 euros, 30 to 40,000 euros. And cutting every tree is not very smart, you know. And in this project, we use technology that uses recordings of the eating sounds of this larva. And then based on the sounds, we develop model of this species. And we also use model of the world, all the sounds that are everything else. All the acoustic background means model of the world. So based on the model of the world and the specific model for this species, we estimate probabilities. And based on these probabilities and some post-processing, we make decision if the tree is infested or not. And that's the machine part. For some specific time period, the machine counts how many events of acoustic events were counted. Okay, so if we, for 1 hour, we have 5 events, probably this tree is not heavily infested. And if for 1 hour we have hundreds of acoustic events from this type, this tree is heavily infested with the pest. And then the authorities decide if to cut it or not, depending on the estimated risks for other trees. And of course, there is the multi-class decision problem where we have multiple models for multiple classes. We could have a detector for apple tree, banana tree, for some other trees, and then based on the signal and the pre-processing and the features estimated from this signal, we can select one of these models and make decision. And of course, for each category, we could have many classifiers. These are different classifiers built with different technology, so they do errors in a different way. And by combining their outputs, we could achieve slightly better performance, because when we use hierarchical machine learning methods, we are able to compensate for some of the errors done by some of the classifiers. And this multiple models per category is useful when we have to recognize group of objects. Let's say birds. I can do this with one single model for birds, but there is small birds, hummingbirds, large birds, and parrots, and very different kinds of birds. So most probably I will have to develop many models for what is a bird, and then combine this and have a model of the group of birds, and then could have the same of fishes, and then could have the same for humans, many kinds of humans, you know, we are quite different, at least it looks like that. And based on the outputs of these classifiers, we could make fusion of outputs and decision and provide the class ID. So this structure shown here is able to transform the information that comes from a sensor into class ID, class 1, class 3, class 4. This is an example of decision making. But things are not that simple. We could have very complex situation when multiple sound events overlap in time and in the frequency range. What you see on this picture is a spectrogram of duration 5 seconds. And this is a real recording from the forest. And what you can see is the different sound events from 6 different species overlap in frequency range and in time. And if you want to build a recognizer that monitors biodiversity, you need all the information. You cannot just discard one of the species. For example, this number 5 is an insect that has periodic sound emissions. The insect is important because it is food for the bird. Here is one vocalization of the bird. Here is second of the same bird, but there is a frog here. You see, number 3 is a frog. Frog is very important also because this is food for another bird, and so on. You need to capture the whole picture. And how this is done? Of course, there are classifiers that are called multi-instance, multiple label classifiers. That these classifiers can give you a list of objects available in the specific recording. And they will say species 1 is a bird called wren, and then species 2 is probably an insect, and species 3 is a frog, and species 4 is something, I don't know what is this actually. And then species 5 is insect, could be cicada, and then species 6 is another insect. I mean, there are classifiers that based on this complicated picture, that's a spectrogram, sorry. A spectrogram means the distribution of energy over time and frequency. So based on this complex picture, a system could really tell what is inside, what sources of information overlap in time and in frequency. This is very complex, actually. This is also kind of artificial intelligence. It is a way of making decisions in a very complex context. It is a way of interpretation of what is here. I will not go into details. I will just finish with one simple example. It is a biodiversity monitoring system that we implemented around year 2012 in Greece. I was working there for some years, and this is the Amibio project. We deployed a large number of stations in the Mount of in the mountain of Imitus. And these stations had microphones, 3 microphones recording in the acoustic range and 1 ultrasonic. And with these microphones, we observed the acoustic activity of more than 100 creatures, able to recognize 40 of them, but still enough to help us understand their behavior. On the long term, with such recording stations, you can actually identify the dynamics of their population. And if you monitor some key species like bees, like insects, like frogs, you can even predict what is going to happen with the population of birds that use them for food. And also, one side function of this system was that it was able to monitor for illegal behaviors. This is on the right part of the slide. We were able to detect events of fire, of shooting. There is illegal hunting there, unfortunately. And there is also this ATV drivers or motocross drivers that illegally drive inside the Natura 2000 area. So we had a real-time system that is able to detect illegal human behaviors in the mountain. And we also have an instrument to monitor the health of each station, and sometimes it needs maintenance here, and sometimes it is working normally, and some stations are close to maintenance. So with this system, fully automated biodiversity monitoring system, we were in position to solve a very important local problem. It was related to enforcement of legal or illegal activities in the mountain of Imitus in Greece. And this is also artificial intelligence, to my understanding, because you have a system that is able to monitor the environment, to analyze and interpret data, to make decisions, and to provide alerts to the authorities. Of course, a fully automated system will do real actions on the field in order to modify, but you know, at this time, artificial intelligence is not allowed to deal with people. So we stopped to alarming authorities. Thank you very much for your patience. I'm really available for any questions now and also later on through email. Please